In previous videos, we've talked about compound interest, how interest grows based on a principal, a certain percentage, and how many times we compound per year. But with all of those accounts that we've dealt with so far, it was this idea of one big deposit at the beginning of the account. So starting with the principal, and then we just kind of let the account do its thing. It just kind of goes and goes and grows, and we just leave it alone. What we're going to be seeing in this section is we're going to kind of go to our account more often, either depositing money in it or withdrawing money from it. So the first part of this, we're looking at savings annuities. So savings would be an account that's building up something. So this is an account that's growing. What makes it an annuity is that we're making equal payments over equal time intervals, like monthly deposits or daily deposits. The idea is that we're putting in money more often. Rather, the previous formulas we've used was the idea of just one big deposit and then leave it. So an example of a savings annuity would be an IRA, an individual retirement account. So like making a monthly deposit into IRA, but then there's also a percentage that's growing with it as well, so that when we retire, it's not just the money that we put in, it's also this money that was gained from interest. So that's where having a good interest rate can be really beneficial, because while we're putting in money to help, really it's boosting that percentage growth coming from our interest. So let's talk about what this looks like, especially in terms of comparing to these compound interest formulas that we've used before. So let's say we deposit $500 at the end of each year. So that's something that's going to happen. It's going to be each year, each month, each quarter. So it's happening more often, and we're doing this for 3 years. So what we're going to do is just kind of track this account. Let's look at year 1. Year 2, year 3. So, at the end of year for 3 years into an annuity that pays 5% simple interest. What is the value at the end of 3 years? And what we'll have here is, while our account is growing based on the interest, it's also growing with these yearly deposits of $500. So let's talk about year 1. So what we would have is nothing until end of the year. So actually, let's call this end of year 1. End of year 1, just those $500 that we deposited. Now, if we're going to end of year 2, then what we're going to have is that $500 from year 1 plus that 5% interest. So I'm going to write that as 500 times 1.05. So we have that 500 has grown by 105%. And then what we have is another deposit. So end of year 2, we're going to make this deposit of 500 again. So I'm going to take that and add on this deposit. So that 500 times 1.05 is what we would see if this was compound interest, like an annual compound interest. However, now we get this extra piece of more money being added on. Then what we're going to have at the end of year 3 is we'll have that $500 that we started with grew by 5% twice. I'm sorry, actually, we have that $500 that grew by 1.05. Then what we have is from year 2, we added on $500, and all of that together has grown by 5%. So we're taking everything, so I'm going to have these parentheses to group 500 times that first 1.05 plus 500, so what we had for year 2, taking all of that and multiplying that by 1.05. So that'd be the idea of taking what we had in year 2 and it's growing by 5%. Then what we also have is this deposit of $500. So we're adding on $500. So just from this, all I want to show is how the calculation differs from our compound interest that we worked with, because what we're getting is this addition at the end of this money that we're depositing at the end of each year, and that's what's changing here. And it's the idea that we're adding money more often than just once with that principle. Okay, let's take a look at this savings annuity formula so that we don't have to break this down year by year, especially like if we're saving up for our retirement. That's probably quite a ways down the line, and I don't necessarily want to see or have to track what's happening year by year for 40 years or what have you. So instead, we want a nice formula to calculate it for us. So here's our formula. So for a savings annuity, and that's important here, is that this formula is for savings, so an account that's growing. We have A equals, and then we have this big numerator and denominator. In the numerator, we have D times, and we're going to need two sets of parentheses here, 1 plus R over N, close those parentheses with an exponent of NT, minus 1, closing those parentheses, all over R over N. So what is all this notation telling us? So A is going to be the account balance. So that's going to be how much money we have in our savings. D is going to be our deposit amount. So like in the example up above, that would be the $500. So we're making deposits of $500. R is the annual percentage rate. It's an APR. Remember with that, they describe it as a percentage. We want to be sure we use it in decimal form. N, so where N before represent the number of times it compounds per year. Now this is going to be the number of deposits per year. So like up above, it was annual, so we would just have N equals 1. But if it was monthly deposits, then we would have N equals 12. And then our last piece is T, which is the number of years that have passed. Okay, so some notation that we've used before with our previous financial math formulas, but just slightly different order here. Really, the trick to this section is being able to plug into the calculator correctly. So that's what I'm going to emphasize as we go through these examples. So I'll be using that Desmo Scientific Calculator since it can organize things really nicely. We just want to make sure we're getting the correct pieces in the correct spots. So we have 3 examples here. So let's go through them. So at age 30, you deposit $150 at the end of each month into an IRA that pays 4% interest, compounded monthly. And then at age 65, we want to know what will the value of the annuity be and how much interest did you earn? All right, so at age 30, and then we're going to check the account when we are 65. So that's telling us the amount of time that's passed. So 65 minus 30, so that's 35 years have passed, so T equals 35. We're depositing $150 at the end of each month. So that means D is going to be 150 and N is going to be 12. We have an interest rate of 4%, so R is going to be 0.04. And we want to know what will the value of the annuity be, so we want to find what A is, and then we'll come back to this question about interest after we find that value. Okay, so using our formula, we're going to have A equals, we're going to separate our big numerator and denominator. And what we'll have is 150, 2 sets of parentheses, 1 plus 0.04 divided by 12 to a power of 12 times 35. And then all of that minus 1, and then we close parentheses, all over 0.04 over 12. And then we're going to take that and just plug it into the calculator. So really, I'm going to copy it how I've written it on the paper there. So in the scientific calculator, I'm going to separate my numerator denominator. And I'll have 150, two sets of parentheses, 1 plus 0.04 over 12. Close those parentheses, and then in the exponent, 12 times 35. And then getting out of that exponent, we'll have a -1, and then close those parentheses. All over, so down in the denominator, I'm going to have 0.04 divided by 12. So I can see $137,059.64. So let's go ahead and write that down. So that's the balance when we're 65, $137,059.64. All right, so how much of that is coming from interest? So let's talk about how much money we've put into the account. So in terms of our money, so without focusing on the interest and the amount of time, well, we do have to focus on the amount of time that's passed, but the idea is that we're going to this account every month and putting in $150. So in terms of a single year, we're taking $150 times 12. So that would be the amount of money that we're putting in each year. So if I want to see how much money we put in over 35 years, I'm going to take 150 times 12 times 35. And just grabbing that real quick from the calculator. That means over this whole amount of time with this account, we've put in $63,000. What we can see is when we're 65, there's $137,000 in that account. So that rest of it is being made up by interest. So what we can do is calculate the amount of interest by taking that balance of $137,059.64 and then take out that $63,000 that we put in of our own money. So just looking at the difference between those two, we can see that $74,059.64, that is all coming from interest on the account. So that was building up over those 35 years and greatly helps out the amount that we can retire with at the end of it. Okay, let's look at this next one. We have a traditional IRA is a special type of retirement account in which the money you invest is exempt from income taxes until you withdraw it. If you deposit $50 each month into an IRA earning 5.6% interest, how much will you have in the account after 20 years? Okay, deposit amount, so D is going to be 50. We're doing that each month, so N equals 12. The interest is 5.6%, so R equals 0.056. And then we're looking at this after 20 years, so T equals 20. All right, so A equals 50, two sets of parentheses, 1 plus 0.056 over 12 to the power of 12 times 20 minus 1, close those parentheses, all over 0.056 over 12. All right. Now, something that's nice about the scientific calculator is that if you're working on a savings annuity problem, you can either start over and just typing everything in, or you can kind of go back to the formula you're already plugged in and just edit it. So I'm going to kind of use the framework of that last question. So like instead of 150, now we have deposits of 50. Our rate is 0.056. We're still working monthly, so N equals 12, but now the number of years is 20. And then just changing that denominator to have a rate of 0.056. And then I'm just going to double check that everything matches up. And that looks great. So we're seeing $22,037, $22,038. That's how that's going to round. All right, so how much will you have in the account after 20 years? So we'll have this amount. So 20 years, I mean, compared to that last account was good after 35 years. This one we're not building as much, but you can see this comparison of like the difference between depositing $50 monthly versus $150 monthly. That makes a big difference here in terms of our final account balance. All right, let's look at this last one here. So we have a more conservative investment account pays 3.2% interest. That's not very much. If you deposit $6 a day into this account, how much will you have after 10 years? And how much is coming from interest? So we have R equals 0.032. We're making deposits of $6 a day, so D equals 6 and N equals 365, and then T equals 10. So A equals 6, 2 sets of parentheses, 1 plus 0.032 over 365 with an exponent of 365 times 10. All of that minus 1, and then we'll close those parentheses, and in the denominator 0.032 over 365. Okay, let's put this in the calculator. So deposits of $6, 0.032, 365, and then up in the exponent 365 times 10 all over 0.032, 365. So $25,808.36. 25,808.36. All right, so that would be how much we have after 10 years. In terms of how much is coming from interest, well, if we think about how much of our money has gone into this account, we have $6 a day. So in 1 year, that would be 6 times 365. And then we're doing that for 10 years. And then we would multiply that by 10. So that would be a total of $21,900. So in terms of interest, if we end up with $25,808.36, take out the $21,900 of our money, and what we'll end up with is, in terms of interest, $3,908.36. That just shows this low interest rate. It didn't do much for building this account. A lot of that account is coming from our own money. The interest rate definitely helps. I mean, after 10 years, it's giving us almost an extra $4,000 in this account, and that's by no means a small amount of money. But it may want us to go looking for another account where we could get a little more interest, which could help us more in the long run.